Oh, okay, something strange just happened with
You are in the
my.
right mode to present.
Okay, but I'm not able to see my presentation now, so
Oh
sorry,
no.
1 second. Let me figure this out.
I can pause the recording. Okay.
Good, if you want to.
Okay. So welcome everyone to the um, Data Inversion and Assimilation Working Group for SWOT. Today we'll have Shoshi. How do you say your last name?
We pronounce it Reich.
Reich.
Yeah.
Shoshi Reich is going to talk about her SWOT data assimilation with a multi-grid adjoint, and then we'll have time for discussion afterwards.
Yeah.
Take it away.
Great. Hi, everyone. So I'll talk first a little bit about what the multi-grid adjoint method is, show kind of a small illustrative example of how it works, and then some very preliminary results with SWOT data at the end. So for those of you familiar with the echo state estimate, this is sort of the basis for our work here. Echo assimilates kind of all sorts of observations, including nadir altimetry, with a general circulation model using adjoint methods to get these dynamically consistent ocean state estimates. It's a 1 degree product, so it's really good at capturing the large scales. But kind of as we know, SWOT captures much smaller scales than this, and so we need to kind of modify our method slightly. We need a high resolution model to capture the same scales that we see with SWOT. And also, since SWOT is global or quasi-global, we're interested in doing adjoint-based assimilation of SWOT data into a global eddy and tide permitting general circulation model. Now, the problem is that traditional adjoint methods become pretty infeasible pretty quickly at like a global 1/12 of a degree scale. So the adjoint method, this might be kind of just a refresher for some of you. We formulate this constrained optimization problem. So we defined our cost, in this case, I'm calling it J. That's comprised of our model data misfit and essentially some regularization term. And we're wanting to minimize our cost J with respect to some parameters or control variables. Here I'm calling them M, subject to our governing equations. So adjoint methods give us the gradient or descent direction in our gradient descent, and they're really nice because they give us the sensitivity of our cost to all of our control variables kind of in just one forward adjoint run instead of having to run many perturbation runs. But the problem becomes like as our resolution increases, our parameter space increases, which has like huge ramifications for the memory requirements that we need. And also as resolution increases, so do our nonlinearities, kind of making these adjoint models intractable. So already we kind of don't use the exact adjoint. We use various approximations that help stabilize the adjoint. Ariane talked about last time increasing the viscosity, and this really helps to stabilize, but doesn't do much for the computational cost. So the idea with the multi-grid adjoint is to replace our adjoint model on a coarser grid. So this gives us like a similar effect as increasing the viscosity in terms of stabilizing the adjoint, but it also really helps reduce the computational cost. It keeps the number of unknown parameters pretty reasonable, keeps the memory requirements reasonable, and really makes it possible to do this. ECMWF does this. They use multigrid adjoints. They use manually derived adjoints though, and we're interested in doing this with automatic differentiation. So kind of just to spell out a goal one more time, we're developing a multi-grid adjoint framework for a global ocean state estimation using automatic differentiation to enable computationally efficient and dynamically consistent assimilation of SWOT data. So, how traditional adjoint methods work, kind of in one iteration, we have our forward run. We run this forward in time, get our model equivalents, compare that to our observations. This gives us our misfit to compute our cost. The cost then drives the adjoint run. In this case, we use AD to get our gradient of our costs with respect to our controls. gives us adjustments, and then we use those adjustments to update our controls, and then in the next iteration, kind of use those and kind of we iterate in this process. So what we're doing with the multi-grid adjoint, as I said, is we're replacing the adjoint model on a coarser grid. So we'll start with some high resolution forward run, and then we take the model equivalents from this high res run and compare that to our observations. And then we use this cost kind of from the high res to drive our adjoint model. We get our gradient on this coarser grid, our adjustments on the coarser grid, and then interpolate those back up to the high res and sort of rinse and repeat. Okay, so I have kind of a small example to illustrate how this works in practice. To do this, I have this kind of small Labrador Sea regional model where my observations are sea surface temperature at the last time step. And these were designed so my observations are warmer than the model, just kind of illustrate how this works kind of clearly. And for my control variables, I'm using daily atmospheric temperature and initial ocean temperature. Okay. So first thing is I ran my high resolution forward run, got my model SST, and I'm comparing that to my observations. So kind of this first step up here. And we see it's negative everywhere. Our model is colder than our observations as we design the problem. Use this cost to drive our adjoint on the coarser grid. And so here we're looking at the gradient of our cost with respect to initial SST. And we see this negative relationship everywhere. To decrease our costs, we need to increase our initial condition. Got adjustments from this gradient, interpolate them back to the high resolution grid, and we see it's positive everywhere. We want to increase our initial condition, make our model temperature warmer to better match the observations. So this works kind of mainly in part because the multi-grid adjoint and the high resolution adjoint are qualitatively similar. So here on the left, I'm looking at the gradient from just the high resolution model. And then here I'm looking at the upscaled one that we were just looking at before from the multi-grid model. And we can see kind of these qualitative similarities. Also, what's really nice about this, this was kind of a simple test case, and so I wasn't too concerned with taking care of all of the small instabilities that we get in the high resolution model, but the multi-grid actually smooths over those, which is really nice to see. And kind of on the right, we're seeing the same story with the adjustments. Okay, so some early results with SWOT data. Before moving to the global model, I'm still sticking with the Labrador Sea to test things out using the MIT GCM Ocean Sea Ice coupled model. I have my forward model at 1/12 of a degree, the adjoint coarser model at 1/3 of a degree, and these are the resolutions that we're hoping to use in the global domain. I have 21 vertical levels, atmospheric forcing from JRA, and I guess something I forgot to mention earlier was that using this multi-grid approach, we need our high resolution and low resolution trajectories to be compatible or kind of similar. One reason is we don't want to introduce any instabilities in the adjoint. And kind of the other thing is that we want our coarse grid adjoints to be physically meaningful for the high res. So I guess taking the last example, if our high resolution model was warmer than our observations, but the low res was colder, we would just kind of get the wrong side with the gradients and it just wouldn't be useful. So kind of a lot goes into getting the model parameters and the bathymetries to be compatible between the two resolutions. One thing to note, you might see in kind of some of my plots that this is kind of a smaller test case, so I'm using closed boundaries, and you might see the effects of that. Okay, so for all of my assimilation experiments, I'm using the same controls. I'm using initial temperature and salinity, allowing for daily adjustments to atmospheric forcing, like atmospheric temperature, precipitation, winds, humidity, and shortwave and longwave radiation. Also my vertical mixing parameter. And I'm doing a 65-day assimilation window from January to March 2024. This corresponds to 3 full SWOT cycles. So in the first experiment, I'm assimilating only SWOT. In the second one, only nadir altimetry. And then kind of haven't quite done yet, but I'm curious to see after this if I then add SWOT data Am I able to get like a further cost reduction? And I'm curious to see like how much more information does SWOT provide? So just kind of a heads up, these are currently running. I have a few iterations done that I was able to get last week and thought it was kind of worthwhile to show results, but very, very early results. Okay, so starting with the SWOT assimilation. So first off, I'm processing the data by smoothing it and then subsampling every 10 kilometers in both the across track and the long track directions. And this corresponds to the resolution of my high resolution model. All right, so in the first iteration, looking at the misfit, I have my model sea surface height compared to what we get in SWOT. And this is for the full 3 cycles, and then our model data misfit. So using the multi-grid adjoint, I'm getting gradients that look reasonable to me. They're stable. To me, this is really exciting. Um, if we see here the misfit, I guess starting where it's negative, so our model sea surface height is lower than SWOT. So here in our gradients, kind of in this negative region, to decrease our cost, we would need to increase our initial temperature, get thermal expansion, increase our SSH, um, and similar story kind of for salt and in the interior. I'm also getting strong gradients at depth, which is interesting to see kind of how much that's propagating at depth. So far, I have 4 iterations done. Cost decreases really nicely. We're looking at the normalized cost, normalized by the number of observations. It's starting to increase again at iteration 4. I'm not too worried about this yet. I'm, gonna let it keep running and see what happens. Um, but when I look at the relative contributions of the different control variables and kind of what our gradient is most, or what our cost is most sensitive to, I see that the initial conditions really kind of take the lead there. Out of all of the atmospheric forcings, the winds are the highest, which I think makes sense for this relatively short run. Um, but I have kind of some ideas about this, but like I said, it's very kind of early stuff we're looking at. So if I look at the depth averaged mean circulation of my unoptimized run, that's what we're seeing on the left, compared to 3 iterations with SWOT data, I see kind of these large changes in circulation at depth, um, which is exciting to see that kind of SWOT is giving that. But when I compare this to an assimilation I did kind of very similar to this, but with Argo floats, I get similar results. Um, so, on the one hand, very interesting that we're getting these similar results as we are with Argo floats. But on the other, I think that there's definitely like a large density bias or kind of something going on in my forward run. So I'm interested to see if I like first optimize my high resolution forward run with Argo floats and use those adjustments to start off my SWOT assimilation. I'm curious to see what happens there. So that's what's coming up next. One other thing that's kind of exciting to see, as I mentioned, I have closed boundaries, and so the unoptimized model here, looking at the sea surface height, we can really see kind of implications of the closed boundaries around this region. And then after a few iterations, it really takes care of that pretty nicely for me, which is great to see. So my assimilation with the nadir altimetry is still running, and the story is kind of the same. So I thought I would kind of skip those results for now. But maybe in the coming weeks, I'll be able to compare kind of the assimilation with SWOT data to this and have some results soon. So I guess the one last thing here, the multi-grid adjoint, we can see the cost going down nicely, and we also get these huge computational savings. For the memory requirements, our parameter space in the high resolution adjoint would be on the order of 10 to the 8. But for the multi-grid adjoint, where I'm running it on the lower res, it's only 10 to the 6, which has like huge implications for the memory requirements that we need to save the state while we're running the adjoint. We also get a great computational speed up. The high res forward run takes about 5 hours on 180 CPUs. Because of various inefficiencies and the way the adjoint works, we can kind of estimate one high-res adjoint would take about 4 to 8 times the length of the forward run. So that would be like a day or two on 180 CPUs just for one iteration. Whereas when I use the multi-grid adjoint, running the adjoint on the low res only takes about 20 minutes on 16 CPUs. So I'm able to finish one iteration in about 5.5 hours, which is a lot more reasonable. Okay, so yeah, next steps, kind of a lot to do here. Like I said earlier, doing the SWOT assimilation, starting from the adjustments that I get from the assimilation with Argo floats to kind of fix maybe whatever's going on in my high resolution model to start. Finish the iteration with the RADS data, add SWOT to that. And then in the more kind of long term, I'm interested to define our cost in the spectral domain. So instead of comparing directly our model sea surface height to SWOT sea surface height, if I can compare the spectral properties of the two, I'm curious to see how that affects the assimilation. And this might be kind of in a two-stage process where at first I compare just kind of absolute sea surface height, and then after a few iterations, kind of do this new cost in the spectral domain. But yeah, kind of more in the future. And then eventually the global domain. Yeah, that's kind of all I have. Thank you all for listening. So wanted to shout out Ariane and Matt. Thank you a lot for kind of helping me get the technical details of this kind of figured out. So yeah, that's all I've got.
Well, thank you. This was great. Questions for Shoshi? Maybe I'll start by asking, you've chosen to do the Labrador Sea, which is
Mhm.
interesting because it's high latitude and it should have a pretty small Rossby radius. Do you know what the Rossby radius is and how that compares with the resolution? Are you expecting the flow that you resolve to be mostly geostrophic?
Um, that's a good question. I do. I I would need to kind of double check that. Sorry, it's been kind of a while since I've thought about the kind of
Mhm.
initial setup of this, but if I remember correctly, I do think the resolution is smaller than the Rossby radius, and so I
Mhm.
do think we're kind of resolving a lot of those eddies.
I have a question, Sarah.
Sorry, you have a
So,
question? Yeah.
yeah, what's always scary about sea surface height by itself is there's you're kind of fitting TNS to that steric height estimate, and
Hmm.
there's essentially an infinite series of possible profiles. Not many of those make any sense physically, but the 40 bar is solving for some physically realistic set of those. Did you look at the subsurface and see if it was looking realistic? Because you can come up with a beautiful looking sea surface height that doesn't look anything like real life in the subsurface.
Yeah, I did that when I was looking at the assimilation with the Argo floats. I kind of compared what was going on at depth, and it did look pretty realistic, which was nice to see. And kind of interesting that assimilating SWOT data is giving us the same results.
Hmm.
But I, yeah, I guess what I was trying to get at is, um, clearly I think there are some issues with my high-res forward model to start with. And so if I can fix those first and then assimilate sea surface height, kind of interested to see what happens from there.
Right. Oh, cool. That makes sense. Thank you.
Mhm.
Can I ask a question?
Yeah, go ahead.
Yeah, first, it seems great that it's working, and yeah, you gave a good argument for the fact that it is. But I guess I'm trying to understand. So at the moment, it's you probably just made some like pragmatic decision about how frequently you're saving, right? Like you have to save the state of the fine resolution some number of times. Do you like understand how, yes, exactly. Like is that decision more important in this situation than it is in just if you just have the same resolution between the two directions?
Yeah, so something I'm interested in but haven't tested out yet is kind of how much that does impact the gradients that we're seeing. Right now I'm saving, and so I'm coarsening also, I guess this is kind of a small detail, but coarsening the kind of saved trajectories from the high res and then rerunning in between kind of in this chunk on the low res grid. And so that's kind of why one of the reasons why they need to be similar to each other. Right now, I'm kind of just taking the limits of the machine that I'm on and how much RAM it has and going off of that. And so I'm saving, I think it's like every 4 hours, and my low res time step, I think, is 1200 seconds, if I remember correctly. So there's still kind of a good chunk, but yeah, no, that's definitely kind of an interesting research question that I want to look into. Mhm.
Yeah, thank you.
Mhm.
Other questions? Shashi, do you have a map of the SWOT tracks over the Labrador Sea? What's the
Yeah,
sampling
sorry,
pattern? What does it look like?
cat's getting in the way. Um, was kind of, so this is after the full 65 days, so three full
Hmm.
SWAT cycles, um, January to March. So this region
Hmm.
is covered by sea ice here.
Hmm.
So we get like, yeah, pretty good coverage.
So the tracks um, go through sort of, how often do the tracks overlap in this at this latitude?
Hmm.
So
Yeah.
you get more than just once every 21 days.
Yeah.
And do you have access to the mooring data in the Labrador Sea, right? So do you have access to that? Does that provide an independent validation?
Um, I I don't know if I have access. It's a good question. I should definitely look into that. Make a note of it. I'm kind of in my assimilation, I'm passively carrying along various different costs
Mhm.
of like Argo floats, and kind of when I'm assimilating SWAT, carrying RADs along
Mhm.
and vice
Mhm.
versa. Um, but yeah, there's definitely kind of a lot of validation I still need to do.
Yeah, with a dozen people here, probably people can come up with enough to keep you occupied for the rest
Yeah,
of your
no, it's
life.
a lot of this, gosh, sorry, my cat. A lot of these results I just got like on Friday, so
Mhm.
definitely a lot
It's
to be
really
working
impressive.
on.
I think one of the interesting things about the Labrador Sea is that there's freshwater input from melt, but you're in a season when you don't expect a lot of melt.
Yeah, that's also something I've talked about with Patrick, is trying this kind of during a
Mhm.
few different times of the year.
Mhm.
Um, it's kind of interesting to see that it is kind of working so well in the winter months.
Mhm.
But yeah, I'm also curious to see kind of what happens later on in the year.
Right. You might imagine that in July or August, you could diagnose where there were big freshwater
Yeah.
impulses coming in off of Greenland as it spurted out fresh water.
Yeah. Yeah, I think one thing that does make this a little tricky is with the closed boundaries, there's just
Mhm.
kind of need to be careful of
Mhm.
some of these things. But
Mhm.
um, yeah.
So, and then other, I guess other work has done, the LLC 4320 is running at something like 1/48th degree. Is that in the realm of possibility? Would that even be
Um,
relevant?
I think we just don't really have the maybe computational power. I don't think we can run a forward high resolution model at 1/48th of a
Hmm.
degree and expect
Hmm.
an adjoint at 1/3 of a degree to still be
Hmm.
meaningful. I think at that
Uh-huh.
point, we would need,
So it would be just massively more expensive.
right. And so,
Yeah.
maybe a 1/6 of a degree. I just don't know.
Uh-huh.
But yeah, the goal is to start with the
Yeah.
LLC 1080.
Yeah. So, and you're thinking about moving to the LLC 1080 globally then?
Yes. Yeah. And then
Cool.
it would be the LLC 270 for the adjoint model.
Yeah, it's easy to get very excited about the Labrador Sea, but I guess your your big goal is not to understand the Labrador Sea, but to understand the globe. Use this as a proof of concept. And so,
Yeah, and part of it too is we'll see kind of how much, me personally, like I'm able to get to the global
mhm,
domain, but
mhm,
just setting up a lot of the framework on the Labrador
mhm,
Sea. And it's nice because we do kind of get the sea ice coupling
mhm,
that we will have to deal with in the global domain
mhm,
anyways.
mhm,
But yeah, the Labrador Sea is a little, it was kind of set up for the multi-grid purpose or the divided adjoint in the MIT
mhm,
GCM lingo. So yeah,
mhm,
that's kind of the history with it.
I think all these things people are mentioning, it's showing, it is as complicated as anywhere. So if it works here,
mhm.
it'll probably work
Right.
everywhere.
Yeah, exactly.
Exactly.
Yeah, the only thing is, not having tides yet. I think that will be kind of a
Mhm.
big jump.
Or like you've just
We've lost Spencer.
have you got me again? No?
Yeah, now, yeah.
Yes, okay. Like you've chosen 1/3 of a degree and 1/12 of a degree, and
Mhm.
that makes sense as a pair of resolutions, but it's not necessarily clear that that will make sense at every location, I guess. Um, I don't know. I mean, because I was thinking about like, could you even apply this even more, right? Like, could you go to 1 degree? And I guess the answer is probably no. If you,
So yeah, I think there's kind of
Mm,
this endless amount of experiments I can run
yeah.
with this, and some of it is questions about the multi-grid adjoint setup versus
mhm,
questions about SWOT. And so, right, I could try this with adjoints at 1 degree, 1/3, 1/6, and kind of
mhm,
see the
mhm.
comparisons between them. But we're kind of choosing right now this kind of 1/12, 1/3 as like kind of a nice middle ground to start.
I think the tides is a cool question. Would there be barotropic and baroclinic tides in the adjoint or just in the forward model?
Well, that, yeah,
Mhm.
that's kind of a big question that,
Yeah.
um,
Do
I,
we
I
know
think
of
it
anybody that runs tides in their adjoint? Do you guys do that at Scripps, Matt?
I,
Yeah, we've never done it, primarily because the time step has to be much shorter when you include tides, and so it gets even more expensive. I don't
I,
see a, I don't know if I see a, I don't know if there'd be a problem with the stability or anything. We've never really tried it.
yeah, I guess my like mind skips ahead to the physics even. Like I was talking about the 3D projection. What do you do when, the swap product tries to take the stationary tides out, but you still have a bunch of non-stationary tides running around, internal tides. So when you feed the SWAT image to the 40 var, how does it distinguish between balanced and unbalanced motions when it's running back and forward? Does that question make any sense?
Yeah, I think wouldn't you have to put the whole SWOT signal in and then solve for the balanced and unbalanced
Well, the
or
adjoint would figure out
the
what's balanced and unbalanced.
yeah.
We'd rely on it, whether it gets it right and how we project that on the control vectors. Um,
But
I,
you kind of have to have some kind. It feels like you'd have to have an image processing to do that, like Sarah was saying, because all your SWAT has such a low repeat that instantaneously you're
we're not.
feeding it just. Go ahead.
We would just give it the raw data. We would just say, here's
Mhm,
the raw SSH with tides and all. Try to take out the engineering errors, but we'd have the raw SSH, and the model would give its raw SSH. And the reason why I'm not like terrified of this is I don't think the tidal processes in the model would be any more nonlinear than everything else going on.
Mm-hmm.
yeah,
So
But
I,
you
I
you
think I
think
think it would work.
you think intuitively the adjoint would see a wave bump in sea surface height differently from an eddy bump?
Yeah, so we would see both. So we okay, so we have done this where we've just done, a single SSH. there's no real difference whether it has a tide signal or not. If you put an
Hmm.
SSH observation in, or you say what's the sensitivity to SSH, you get the adjoint gives you everything that can affect
Hmm.
that SSH. So it gives you barotropic waves,
Oh,
even if you don't
I
have
see.
barotropic waves in your forward model.
Okay.
We filter those out by not letting them project in our control vector. But all those dynamics are in the adjoint already. It gives you near inertial waves already. We filter those out by saying the winds can't have that super small scale structure that would force them. So there's actually no numerical difference, I feel like, by giving an SSH that's, you know, 1 centimeter or 1 meter. It's a
Hmm.
bigger forcing. But if the four, when you're differencing it from the forward model, if the first guess barotropic tides were close, then you shouldn't be giving it. I guess you are amplifying the signals. So
Hmm.
yes, there's more chance to go wrong because you're just hitting it harder. But
Hmm.
physically, there's no difference in the dynamics of the ocean.
That's cool.
Well, maybe I guess a question or to clarify, Matt, kind of in this multi-grid context, kind of we're just getting, I mean, we're mainly focusing on the large scales and hoping that kind of the small scales come along with it. But um,
Yeah.
yeah, I'm curious how your thoughts change with the multi-grid.
With regard to getting to higher and higher.
Yeah.
Well, I mean, when they do this in the atmosphere, what they're often looking at is how different can the grids be? Can it be 10 times coarser, 5 times coarser, 2 times like how? Because if the fronts and the dynamics are very different between the models, then the sensitivities and the gradients will be very different, and it won't work. So at ECMWF, they run it with the adjoint 4 times coarser than the forward, and they found that works. What that suggests to me that probably 8 times coarser doesn't work.
Right.
Um, so if you want to run at a sixth of a degree, you probably get away pretty well with a 1/3 degree adjoint, maybe even a half a degree adjoint. And we know we can run the adjoint at a third and a half. If you want to run at 1/48, maybe you need a 1/12 degree adjoint. We know the adjoint's not very stable. The dynamics at a 12th degree are pretty crazy after a week or two. Um, so I think it all just depends on how nonlinear the I think there's a lot of value in coursing your adjoint. We like to smooth it anyway. It runs faster. You're doing great work showing it's moving forward. But how you design this tool for the exact problem, it's just there's just things to consider, and it all comes down to nonlinearity, I think. I see Ellen is
Yeah,
talking.
Ellen.
Also, I had a question sort of about that already, and now you're talking about it. So, um, given that this already is done in the atmosphere, is there any kind of literature on how much these things can diverge? Because wouldn't you expect that there could be like a map that varies with latitude of how much, just knowing that it's been implemented in the atmosphere for a while. I'm curious, Shoshi, if you've seen anything like that. Like you'd expect that knowing the dynamics, you might be able to say how much the forward and the
Yeah.
reverse paths can diverge.
A little unfortunately, there's not a lot of
Yeah.
literature about this. This
It
has
seems
been
it
very
seemed
frustrating for me.
There
optimistic,
should be.
but
There
Um,
should be. That
yes,
might be your
there
Who's
job.
should
doing
be.
it? Is
Unfortunately,
anyone doing it besides ECMWF?
not that I've been able to find. I've found kind of old echo related papers where Matt, you might actually be an author on the one sticking up, where they like use the adjustments in a higher res, but they're not kind of doing this multi-grid adjoint, but that's okay.
yeah, it seemed optimistic. But I was just curious if anyone had yeah, tried to
There was
quantify that.
big talk about this. This was kind of a fad. Everyone should do this. I feel like 10 years ago, and ECMWF when they first started doing it, and then I haven't heard about it since, except Shoshi.
So yeah, it might be. I think I'm gonna have to be the one to update about it.
Well, in that regard, you're you said it would be much more expensive to run the adjoint at the full resolution. Is there a
Mhm.
possibility of doing a test case and just looking at how the adjoint behaves differently if you run the
Yeah.
much more expensive version?
Yeah, I'm definitely meaning to do it. I've run the much more expensive high-res one on for just a 5-day assimilation window and saw some instabilities there, but it was able to run. I didn't have to increase the viscosity. It was kind of okay.
Hmm.
Um, I definitely kind of in the works, maybe even this week, want to run kind of the high resolution adjoint for the full 65-day assimilation window and do some comparisons.
Yeah, that would be really interesting.
Even just one iteration, I think,
Right,
can
just
give
one
us a lot.
iteration would be enough to
Yeah,
show how the two can
right.
diverged.
And if it takes 2 days,
Mm.
it's fine. I'll just, yeah.
That's what weekends are for.
And I
Yeah.
also I want to mention one thing about running the adjoint with the tides is that we get you get such a huge speed up because if you run a model at a quarter the resolution from the DXDY, you get like 16 times. Or no, that's is that so what's the CFL? Did you show this? It goes directly,
Um, where is it? Here. But yeah, just some raw numbers.
but just from the CFL scaling, it should go with DX. So you get 4 times faster with the if you go to a quarter of the resolution, I think. And then, but the other thing is when you go to coarser, you can run with a longer time step if you're not using
Yeah.
tides.
Yeah.
So then if you so the at a half the resolution or a quarter of the resolution, your time step's like 3 or 4 times longer too. So you end up with like a 16 times speed up.
Yeah.
It's like a order of magnitude. And all of a sudden the Ford model becomes more expensive than the adjoint.
Yeah, that's
Mhm.
exactly what I'm seeing is kind of this
Mhm.
huge difference between the forward model,
Is that what you're getting here? You're
five
getting five
hours,
times.
180 CPUs, and then 20 minutes on just 16 CPUs for
One
the
more.
low-res
Okay.
ad point. But something, yeah, I guess going back to Spencer, your
Looks
point
like more than an
before.
order of magnitude.
Yeah, it's
Yeah, no,
crazy how
it's
fast the
crazy.
adjoint's like just this, it's
Yeah.
like yeah,
Can't afford not to run it.
it's so
Um,
cheap. Yeah, except that we need more Shoshi to get it all working.
um, yeah, and just I guess a technical detail. I'm not sure if this is interesting to folks, but because of this difference also in time steps, the checkpointing is just kind of a lot of bookkeeping. But then if I guess I'm the state that I'm running within one checkpoint, it is fewer time steps on the lower res model. So that also kind of helps keep the two in line with each other.
Yeah.
This is really nice. Thank you.
Yeah, thanks
Yeah.
for this.
Any other discussion points for this? And if not, maybe I should ask broadly, um, if people heard anything recently at Ocean Sciences or elsewhere that we should make sure we bring out in this working group, or anything that's on anybody's mind that should be shared. I feel like the topic that we haven't heard a lot about yet is um, the AI assimilation with SWOT, and hopefully we'll get somebody to talk about that.
What do we anticipate that looks like?
Some sort of neural net with um, taking SWOT data in, training on the data, producing a
I,
field.
uh,
Do
so
you
are
know,
you
Spencer?
talking about Tatsu's work particularly, or just in general?
I know there were at least one thing presented. Yeah.
So I don't know. I think this is sort of interesting because it's a question of like what is assimilation, and
Mhm.
if you can persuade people that this is assimilation, then it belongs in here. Right.
Well, this
And I
group
think
is
yeah.
data inversion and assimilation. So
Okay.
I think anything that leads to mapping and filling gaps.
Um,
So
but yeah, both Tatsu and Scott Martin are
yeah.
working on these methods, which are basically generative, right? You train your generative model to create either sea surface height fields, or I mean, in Scott's case, he's creating fields of everything from LC 4320, and then you just condition. You do some conditioning, so when it generates the fields, it has to get them to match the SWOT observations, and seems like both of them, I don't know, certainly Tatsu is in a situation where he could give a talk, I think, about this. I think
not
Scott's
them
probably a little
updating.
further.
They were doing optimal interpolation of observations. They weren't updating a model.
Well, no, because there is no model in some sense. There is no model, right? There's a generative algorithm, and yeah, so it's all just conditioned. You're sampling from your probabilities, based
drawing
on
the statistics from a model and then figuring out how to gap fill or map from that.
So the training data set included a model.
Yeah.
Yes.
A general circulation model.
Yes. Yeah.
Okay.
Yes.
That makes sense.
And this gets people excited. It gets lots of headlines, and there's questions then about how to validate it.
And was the training data like a free running GCM and SWOT, or was it assimilated into the GCM?
So yeah, for these, it's just LLC 4320, right? So it's forward running.
With a
and I guess this
superenergetic
also,
tide. And
yes, this also makes me think of right, there's also this go flow thing that people are talking about, right? Which is, I guess, led by Luc Lenain. That is not technically SWOT, right? Because they're not actually using SWOT, but they're doing a very similar thing, right? Although not exactly the same, because I think it's not. Yeah, it's not exactly the same somehow. I'm trying to understand why that is. They somehow, they're not. It's not as generative in the same way. But yeah, I should go back and look.
So I mean, as a modeler, it's kind of scary because if they're training on the model, that means they're dragging around all the problems the model has.
yes. Yeah. And so the next step beyond this would be to merge the physics with the AI. And that's probably why, as a community, we should be talking about this and not running away from it.
I agree. So you're saying physics from the observations?
Physics from physics, physics from the model, physics
I mean,
from the Navier-Stokes equation.
But I mean, the general circulation models are just an approximation of those physics.
Yeah. So
So,
the best
with
representation of the physics as you learn it from the data or from our understanding of the physics, plus the statistics.
See, that makes me
from
think
the AI.
that the AI is just like a reduced order model. You have to spend a lot of computer to run the full GCM, and by training on the back end, you just get a really quick solution from the AI in the present. Or is there something magical with the generative word going on here?
I think your description sounds good.
No, my understanding is that what you're saying, the AI is just a surrogate model, right?
Yeah.
That's how I see it. If
Yeah.
you're
The
training,
problem is that if you're not careful, it gets spurious relationships, non-local covariances. So you have to be careful.
if you're training on the GCM, I assume that your AI is a facsimile of the GCM.
That's what they want. They want a cheap
Yeah. No, I
facsimile.
agree.
Yeah.
Well, I mean, I'm being cautious because some people in the future will get overconfident about the AI. They'll be like, "Wow, this is amazing," and it is.
In the future, you mean next week?
Yeah,
Yeah,
you mean
next
last week.
But then
No,
the
I mean the
network.
issue, and we've tried to look at response function. And the issue is that these work for some things, but also they just are doing regression to get essentially to get the facsimile, and so they'll think that what's going on in Labrador Sea is sensitive to what's going on in the Ross Sea.
Yeah, I think those are different methods than what I'm talking about.
Okay.
Right. It's true that if there are AI models, right, that are really the goal is to do future prediction, right? And
Yeah.
but basically, right, what I'm talking about is gap filling between observational
Mhm.
transects, right?
But that
And
makes me
so
more nervous, right? Because then your assumption in that is that the GCM is really good, which
yes,
I think they are, but you're using the model physics to fill in the gaps of the observations, and the model isn't always a good predictor of the real Earth.
That's what we're
I
doing with
think
the simulation.
yeah.
Yeah, the question
We're
is, do
trying
you
to do
need to
that.
know statistically what's the likelihood of having an eddy, or do you need to know where the eddy is?
Well,
I
and
mean,
you're using the
Matt kind of
model
makes a good point.
physics, but you're
I'm
using the
sorry.
model physics from another point in time. So
Mhm.
like when we do 40 var, we're using the model physics that aligns with the data. But when you do the generative AI version, you've trained on a history from the model. You're generating a new state that is theoretically aligns with the data, but you don't know if the dynamics you're seeing in that data were ever actually present in the history.
Yeah. And
So
I
I
think,
think,
oh, sorry.
yeah. Well, so I
Oh,
think that's why Matt is not being fair to his own methods, which are that like 40 bar does just do the same thing, except for the fact that you know you've aligned the model physics in time with the observations as opposed to using a historical training set.
Hmm. That is a good distinction. But I mean, also just to give the devil his due, the 40 bar is kind of there's literally a cost function, and all these things are trained on as a cost function in the neural network, right? So the 40 bar might actually be a decent analogy.
Mhm.
yeah. I think a big difference is with 40 var, we can like close budgets, and with this generative AI, think you need to be like really careful about what you're seeing.
Mhm.
Yeah, I agree. Let's charge forward on AI with a healthy dose of skepticism.
I think
Yeah,
also arguably for Diva is AI. It's just we we didn't call it that. It was invented before.
I kind of agree. Like I said, that all the core algorithms of neural networks are in
Mhm.
the
The,
adjoint.
the huge difference, though, is that yes, we're just looking for our biases and what do they call them? Weights and biases. We're just looking for those two things on each of our neurons, but our functions that are projecting those aren't just sign functions. They're actually discretized model physics. So it's a flavor of AI.
Yeah.
Mhm. Given the national priorities for um, AI, AI and quantum, that's apparently
Yeah.
all we're allowed to do now. So,
Yeah.
so we
And I
probably have to
thought,
repackage everything we do as one or the other,
but yeah,
or
fundamentally, I
both.
don't think there's really any difference between training CNN and training, well,
Mhm.
our
Mhm.
assimilations. It's a little bit more complex under the hood for us.
I think the other thing is in response to Ellen's point, Tatsu actually has some really nice examples of where um, he's trained in some area, he's transferred to another area, and some portion is inside right the probability distribution and it looks great, and then some place in it doesn't work, right? And I
Mhm.
think he's actually in some ways we actually, I mean, yeah, this would be a thing that we could ask him to also focus on if you want him to give a talk, um, to talk about both right the strengths and the weaknesses, and I think that's one thing that Tatsu's really good at actually.
Yeah, well, it
um,
gets complicated, and you have to know that as you teaching your model or whatever we want to call it.
Mhm.
Because yeah, if you get the adjoint response functions to the ocean in like off California in February, they'll work really well for March. They'll work really good for January, but they're going to give you big biases if you apply them in August because the stratification's different, everything propagates differently, and so there is a difference in the ocean statistics seasonally and
Mhm.
regionally, and we just
And interannually, right? Like you got to get how many ENSO cycles do you need before you? I mean, the California current will get affected by that, right?
Mhm.
Yep.
Yeah. Well, I think this series is scheduled through June, and we have to figure out if we're going to take July and August off. The SWOT meeting is in September, I'm told. I think
Any plans for OSTST in general, or you're just sticking to SWAT? It's in Germany.
it's in Germany. The OSTST is the third week of June. Yeah.
Yeah.
Uh, somebody will go.
All right, good. I
In my
wiggled my way on one of the sessions, so if someone we can grease the skids if anybody needs help.
Yeah, I'm trying to negotiate with my family and Salosaurus, who's in my OSTST funding, to figure out who's going to go and how.
Awesome.
But yeah, the SWAT meeting I heard rumor is going to be in Boulder in early September.
Cool.
So that's total. That's the nominal agreement according to Tom. And I'm probably not supposed to say that on a recording, but because I don't think they've signed anything firmly. But that's sort of what people are targeting.
Mm-hmm.
So yeah, so we could think of, for this series, we can think about whether we're going to put a speaker in for July or take the summer off and pick up after that. Mm. We can stop here for today, I guess. This has been a great discussion. Thank you, Shoshi, for setting it off. Everybody else for having things to say. And
Thanks. That was fun.
next month, we are skipping the first week because it's Easter Monday. So we'll team up with the high resolution modeling group on the second week of the month. So
Thanks, Sarah.
see you all later. Bye.
Bye.
Thank you.
Thanks.
My mouse.